3.4 Descriptive Measures of Population. So in this section, we're going to look at everything that we have looked at so far, just about in sections 3.1, 2, and 3. The only difference is now we're going to transpose everything that we've learned in terms of sample statistics and turn them into population parameters. So what I have on the left side here, to the left of the screen here, I have the list of the things that are relevant to our work going forward with the sample. So I have handpicked the sample size, the sample mean, the sample deviation, and sample variance. We're going to stay with these four going forward to future chapters. And to the right, I actually have those same four pieces of information, same statistics, if you will. Got to be careful how I speak here, because when we talk about statistics, we're talking numerical measures of the sample. So I should say we have those same attributes rather than statistics, same attributes as they pertain to the population. So for example, the sample mean, X bar, translates into the Greek letter mu, like again the sound of a cat, mu, for the population. The sample standard deviation turns out into sample or population standard deviation, and the sample variance turns into population variance. Now the notation sigma is what we've used in here for both of these, right? And this is the second and the last sigma in the Greek alphabet that we're going to look at. The other sigma was the mathematical operator that we use in chapter 3 when we earlier sections of chapter 3 when we calculated the sample mean. Now the formula, I have them here for you. The formula for sample mean, that's X bar, okay, and this one is right in here. X bar is sigma X over N. And the formula for the population mean, you just change the notation from X bar to mu. This means you're now doing it for the population. And there's a change in the denominator from N to capital N. But the numerator, both of these are adding up, so we don't need to adjust the numerator, only the denominator. Both of those sigmas in the numerator means you simply add those scores up. When you look at the other formulas below it, S squared, in section 3.2, we looked at this one. S squared is sigma x minus x bar squared divided by n minus 1. The population counterpart to that is exactly the same. X bar is replaced by mu, and instead of dividing by sample size minus 1, we divide by all of the population, not n minus 1. That's actually capital N. And the standard deviation is just the square root of the variance. So I just show it as a square root. Now StatCrunch will do this. I'll show you how to find these standard deviation for the population, the standard deviation for variance for the population in StatCrunch in a few minutes. And let's finish this section by actually talking. This is rather short, brief section for us. So we're going to talk about the standardized variable, or a Z-score. Okay, a Z-score is what we call again a standardized variable. And that's all that is. Now, what Z-scores do for us, do for us is that they take the scale and the units out of the random variable. Okay, so for example, if my random variable is the weight of a breed of cat or a weight of breed of dog, when I standardize those scores, I simply have numbers that have no scale. So usually weight is measured in pounds. The Z-score for weights has no scale. So that means it is not in pounds. It's just an index, a number. That's all that is. Okay. So what is a Z-score? A Z-score simply indicates a measurement I should say a measurement's position. That's all it does. It looks at the relative position. A position or a measurement's value relative. The key word here is relative, means in relation to. Relative to the distribution's mean or average. It looks at everything relative to the center of the data, okay? And it does it in units of standard deviation. Okay? So it's going to, in other words, it's going to translate into like, okay, well, what is your score or my score relative to the center to the mean? Are you 1 standard deviation above? Are you 2 standard deviation below? Are you half a standard deviation above? So that's how we interpret the z-scores. How far from the mean you are? Are you above or below the mean? And how far in terms of a standard deviation? So when we talk about a z-score, if a z-score turns out to be 0, then therefore the score equals to the mean. Okay, so a z-score of, if my z-score on my exam, let's say was 0, that means I was the average. And we'll see the reason in a moment once you see the formula for the z-score here. Let's see, so we're going to talk about a z-score that is positive. If it's positive, that means the score, the actual score, is above the mean. We're talking about the score here means the value of the variable, okay, or the measurement. It's above the mean. And if a z-score of a value turns out to be negative, that means simply the score is below the mean. Below the mean. And that's all that is. Okay. Now the formula for z-score, by the way, now z is using population parameters now. Okay, it's going to be x minus mu divided by sigma, and that's what that is. So for example, I'm going to make up 3 scores. Let's say my score is 80, somebody else's score is 85, and another person's score is 95. Okay, all made up. And let's say the average here is actually 85. Okay, so now let's actually turn these scores into z-scores. So, and I make up the standard deviation for simplicity to be 5. So a z-score, my score of 80, z sub 1 is now going to be 80 minus 85 divided by 5. And that z-score turns out to be negative 5 over 5 or negative 1. Okay, and all that means is that I am 1 deviation below the mean. My score is 1 deviation. See, negative z-score means I am below the mean. Okay, and that's all the z-score does, really. There's nothing to it. A z-score, the middle one, z sub 2, for someone who scored 85, or the measurement is 85, minus the mean divided by sigma, and this makes 0 over 5, and this is 0. So notice 85 in this case is the same as the mean, right? And that's what this top item told us. And finally, for x sub 3, this person's z-score is going to be 95 minus 85 divided by 5. This person's z-score is going to be 2. That means this person's score is 2 standard deviation above the mean. Okay, so that's all we really are interested in with z-scores. Now, let me actually go to StatCrunch, and again, this is all it is. And we're going to now go to StatCrunch and actually take a look at and see how we can get these population measures. My focus is going to be on population deviation and population variance. Okay, so this is the exercise that we're going to take a look at, and we're going to do this in StatCrunch. But let me just kind of read over this quickly. This data is from the ESPN website. Okay, and looks like these are the weights in pounds for the players on the basketball team for the 2008 to 2009 season. So it looks like there are 2, 4, 6, 8, 10, 12, 14 scores here, right? So it looks like their size is 14. Now, the question reads, obtain the following parameters. So notice that we're going to treat this as a population, because since this is the 2009 players, there's only 14, so that is a population. They're not a sample for the year 2009 of Dallas Maverick players. This is the population of those players in that season, 2009 season. So let's take a look at now how this works. Okay, use appropriate mathematical notation for the parameters. So in part A, first the notation, we want to know what mu is. Okay, so mu is there. And in part B, and we're going to get this from StatCrunch, I'm not going to do it by hand. Standard deviation, parameter means population, that's sigma. Now C, the notation for median, let me just show you, but the book doesn't show it, is mu with a tilde on top of it. That will be the median. And of course mode, D mode, we go capital MODE, and that would be for the mode. And finally for IQR, now these are population information, right? The only formula that's sensitive to population, and we had to adjust it for the population parameter, was the formula, look up here, is the formula for standard deviation and the variance. Okay, and that's what these are. We don't need to really make any adjustment for sample mean. Again, the difference is instead of dividing by 20, 30, 50, you divide by 20, 30, 50 million. So the adjustment was in the notation for capital N being the population. So when we go to StatCrunch, we're going to get everything like we did before when we go to StatCrunch. Okay, the only one that's actually going to be affected because there's actual change in the formula is sigma. Okay, so let's take a look at StatCrunch and see how this is done. Okay, so I'm in my MATLAB and I went in and clicked on StatCrunch, and this is what I get. Again, I like to use data sets from your textbook to get into StatCrunch, and this actually does give me data sets, but let's see, for this exercise, this is exercise number 162. So if I go to chapter 3, exercise number 162, this way I don't even have to type it in or anything. And there you go. Exercise 162, Dallas Mavericks. So these are the weights, right? These are the weights. And let's get those numerical measures. So we're going to do it like we did in earlier section 3.1 and 3.2. So we're going to go to Stat. You go to Summary Stats. And our variable appears in the column. So we go columns. There's only one variable weight, so I'm just going to left click once on that. Now in here I have a whole bunch. You see all of these statistics that are available to us. Now to select more than one, look at the highlight directly below it. It says to select more than one. You can do it with shift click or control click. So let me actually do that. So I'm going to go on, okay, I've already left click on N. Now I'm going to hold the control button on my keyboard. I'm holding control and I'm going to click on the mean. Now remember, there is no adjustment to the formula for the mean other than the denominator is capital N. So StatCrunch doesn't even care if this is population or sample as long as you and I know what they are. Now, we're looking for sample deviation I'm sorry, population deviation, and I'm also going to do population variance, both of them. Now, do not click on these. These are sample variance, sample deviation. We do not want them. So just go down, and we're going to go to median. No adjustment to the formula for the median. Again, instead of lining up 20, 30, 50 scores from low to high, you're going to sort out 20, 30, 50 million scores, let's say theoretically. So no adjustment to the formula for that. Minimum, max, we don't need. Now IQR, the same thing. Quartiles, these are all based on the ordered statistics that we use, so there is no adjustment in the formula. So how are we going to adjust the formula for deviation and variance? And there you go. UNADJ means unadjusted. So this is the unadjusted standard deviation and unadjusted variance. And this is how the statisticians call it. I'll explain this unadjusted versus adjusted in a moment when I go back to my note. But for now, let's just take these numbers out and carry them with ourselves to my notebook. And there you have it. So the population mean, median, IQR, unadjusted deviation, and unadjusted variances is what these are. I'm just going to transpose these, transfer them to my note, and I'll explain the adjusted versus unadjusted in just a moment. Okay, so here we are. Now I just copied that information from StatCrunch onto my note. So let's answer the questions. What is the population mean? The population mean is right in here, 223.4. Okay, 223.4. That's our population mean. And these are again the weights in pounds. Okay. What is the population deviation? We're going to look at the unadjusted standard deviation. That's what sigma is. It's 28.1. And the population median is 221.5. Remember, for mean, median, mode, IQR, for these, we do not adjust the formula drastically. The conceptual adjustment is made in that instead of, again, small, we do this for large groups. The mode I don't have, I'm going to get it directly from the data instead of going back rerunning this. The IQR interquartile range is 30. And there you go. That means the middle 50% of the scores of these 14 scores, the middle 50% range in a 30-point range. Okay. And we can actually verify this in just a moment. Let me, in fact, explain the... let me find the mode first. So mode is most frequent. I have 175 and then 180. Those are the low weights. Wow, everybody else is above 200 pounds. So there you go. Now let's see, 210, 240, 45, 30, 18. So I don't see actually any weight that repeats except 210. There you go. Unless I'm looking at it incorrectly. 30, 60s, 35. No. That seems right. So if you find something other than that, you can correct it. But I think that's right. So the mode is 210 for this exercise. That means the most frequent weights were 210. Not many, just a couple. Enough to qualify for a mode. Now, the adjustment I was telling you about is this. When we look at the formula, and right in here, remember the formula we had was x minus x bar squared over n minus 1. This was for sample variance. Sample variance. And for population variance, it was sigma x minus mu squared over n. So what we have done, in fact, the original formula for everything for the population is the original value that we're looking for. Remember, sample comes from the population. First is the population, then comes sample. So all these original statistics belong to the population. So in the population, the formula actually requires that we know mu. Well, we don't know mu in the sample, right? We don't know the mu for the population. So when we use a sample, we make an adjustment, and this is the ADJ, or adjustment that is made for mu. We change it to X bar. And of course, we do make an adjustment for the population size becoming sample size. But the key formula, in the formula, the mu that's adjusted for by X bar, that is the adjustment that is talked about here. You see that? So for population unadjusted, therefore unadjusted variance, that means before you replace mu with X bar. Okay, unadjusted variance, that's going to be sigma squared. Adjusted variance, that's the sample standard deviation. So when we say adjusted variance, which normally people don't say adjusted variance, but in this context I am. Adjusted variance, that's just sample variance. It is again adjusted for mu. Okay, so I want to mention that. And okay, and the IQR of 30, again the middle 50% are in a 30-point range. So let me actually show you this now. Okay, so I went ahead and actually grabbed the quartiles. There you go, quartile values here from StatCrunch. So these quartiles are 240. So I'm just going to go to 40 here. And 210 actually is the second, 210. Now, if you count the number of scores, including these two and between them, there should be 7 scores. 1, 2, 3, 4, 5, 6, and 7. You see that? So that's what that middle 50%, the middle 50% here is in the 30-point range. And then there's 25% for a total 100%. So again, the idea is that, so what is that telling me again? If you look at these middle 50%, their weights don't tend to fluctuate as much as if I just look at the range between the low and the high guy. Okay, that range is much wider, right? That's 105-pound range as opposed to 30-point range. So again, it shows us, it tells us or shows us about the stability of data points, in that they are more stable near the center of data set. And that is it. So pretty light-hearted section. Again, there's not much. And let's see, I think we answered everything here. So we are done with this section. Oh, one more thing, because the question didn't ask for it, but let's actually do a Z-score. Okay, just to kind of see how that works. Let me take a look at this person's Z-score. A Z-score for the person that weighs 175 pounds. It's going to be X minus the mean. The mean was 223 pounds, right? Right in here. Now I'm rounding it just to make it easy. Standard deviation is 28. Again, I'm rounding that number. Okay, that number is also inside the box. That's gone. The box is gone. Now, I need to calculate the Z-score, which is easy to do. All I have to do is just do the numerator, 175 minus 223. That would be negative 48 divided by 28. You get a Z-score of negative 1.7. So this person's weight, 175 pounds, whoever that player is, his weight is almost 2 standard deviation below the mean. It's not in pounds. Okay, so it's just that. It's just how far from the center that person is. So if you look at the center of your data, this is the center. Z-score, that's Z-score. Z-score would be 0. Negative 1.7 means 1. That's 2 right in here. Let's say this is negative 1.7 deviation. Each deviation is going to be 1 unit. I mean, you can make the tick marks 1 deviation apart. This particular person's weight is negative 1.7. So he is 1.7 deviation below the team's average. What about the highest weight person? The one that weighed the most was 280 pounds. Let's look at the Z2. That person's Z-score is 280 minus the average was 223 divided by 28. Okay, now 280 minus 223 equals 57 divided by 28. This person is a little over 2. I'm going to go 204. A little over 2 standard deviation above. So if you look at again this person's, here's a Z-scale. This is the center of your data where the 0 is. 1, 2, just a hair over right here. That is 2.04. That's how far this person's weight is above the average. So one person is below by almost 2, the other one is over by a little over 2 deviations. Okay, and with that we come to the end of this lecture. So we are done with section 3.4's lecture.